Here is a compound that plays an important role in E2 mechanisms. Do you know what the name of this compound is? Here's the answer. This compound is called tert-butyl oxide. Let me show you why this is a logical name. Now, notice that this carbon is tertiary. This is a tertiary carbon. It's attached to 3 other carbon chains. That's where the tert comes from. Tert here stands for tertiary, because this carbon is tertiary. Do you remember how many carbons does bute indicate? You should know that bute is the root for 4 carbons. Butane has 4 carbons. Well, notice that there are 4 carbons total. There's 4 carbons total in this compound. That's why we use the root bute here for 4 carbons. And clearly the part here that says oxide refers to the O-. So we can see why this compound is called tert-butyl oxide. Now, please pause the video and see if you can figure out a good name for this compound. Did you try that? Did you realize that this compound is the same compound as this one? These are the exact same compounds, just written in different notation. So this is, again, tert-butyl oxide. This compound is tert-butyl oxide written with bond line notation. And this compound is tert-butyl oxide written in what's called condensed notation. Again, notice that this carbon is tertiary. This carbon is tertiary because it's attached to 3 methyl groups, tertiary. Notice that there are 4 carbons total. 3 carbons in the methyl groups, and this carbon makes 4. That's why it's called bute, because of the 4 carbons. And again, there's an O-. So these are 2 different notations for the same compound, tert-butyl oxide. Tert-butyl oxide plays an important role in E2 mechanisms. So you need to be able to recognize tert-butyl oxide. Please pause the video and try this problem. I hope you actually tried this problem on paper. You won't benefit much from this video series unless you're trying the problems on your own. Now we can go through the problem together. Let's start by numbering all the carbons. I numbered the carbons, including this one. On the other hand, it's difficult to number these carbons because these actually represent 3 separate methyl groups, so I won't bother numbering those. And this is an alcohol solvent that turns out won't participate in the reaction, so I won't bother numbering those carbons. Now, did you notice the ionic bond? K stands for potassium. Potassium is a metal. Oxygen is a nonmetal. A bond between a metal and a nonmetal is an ionic bond. So we have to recognize this is an ionic bond. Potassium is a metal from the left side of the periodic table that wants to give up electrons, so the potassium ends up with a positive formal charge. Oxygen is a nonmetal from the right side of the periodic table, high electronegativity. It pulls the electrons in the ionic bond towards itself to give itself a negative formal charge. Always watch out for ionic bonds, and if there is an ionic bond, you must draw the formal charges, because the most important factor in organic chemistry is formal charges. I hope it's clear to you that there are no ionic bonds here. All of these atoms are nonmetals, so there's no ionic bonds. All these bonds are covalent, so there's no formal charges to draw in here. Now we can start assigning some roles. Well, we should focus especially on the atom with the formal charge. When we see a negative formal charge, we expect that atom to be a nucleophile or a base, but we don't know which one yet. Now, we do not expect the positive potassium to participate in the reaction. Remember that when you see a metal with a positive formal charge, like sodium or potassium, that's probably an unreactive spectator. So this will not participate in the reaction, but we do know that neutral iodide is a good leaving group, which means that carbon 1 is our alpha carbon because it's attached to the leaving group. So we can identify that we have a primary alpha carbon. Carbon 1 is a primary carbon attached to one carbon chain. And now we can determine the mechanism. How do we determine the mechanism? Using our table. We have a primary alpha carbon, which puts us in the top row of the table, primary alpha carbon. Keep in mind that the alpha carbon here is carbon 1. The alpha carbon is not carbon 7. Because in this context, we use the term alpha carbon to refer to the carbon attached to the leaving group. Carbon 1 is attached to the leaving group. Carbon 7 is not attached to the leaving group. So we don't use carbon 7 to figure out which row of the table we're in. We use carbon 1 to find our row of the table. Remember that in this table, the alpha carbon refers to the carbon that's attached to the leaving group. And our nucleophile or base is O-, and we find O- here in the right-hand column of the table. Well, O- and a primary alpha carbon, that looks like it would be an SN2 reaction. But wait, notice that there's an exception in this cell, and the exception occurs when we have tert-butyl oxide. Well, that's what we have here, isn't it? Did you recognize that this is the condensed notation for tert-butyl oxide? This is the condensed notation for tert-butyl oxide. Again, it's called tertiary because carbon 7 here is tertiary, attached to 3 methyl groups. It's called butyl because butyl refers to 4 carbons, and there are 4 carbons total in this compound, 3 methyls and carbon 7. And it's called oxide because of the O-. This is the condensed notation for tert-butyl oxide. Technically, I guess this compound would be called potassium tert-butyl oxide, but we don't really care about the unreactive spectator ion. The reactive portion of this compound is tert-butyl oxide. Well, the table tells us then that here we're applying our exception. We have tert-butyl oxide, and we have a primary alpha carbon, so the table tells us that the mechanism is actually E2. Make sure you write down the name of the mechanism. Why does tert-butyl oxide give us this exception? Well, I'll just give a brief explanation for that. Tert-butyl oxide is a very bulky base. These 3 methyl groups add a lot of bulk to this base, which creates a lot of steric hindrance. And because tert-butyl oxide has so much steric hindrance, it is difficult for it to participate in an SN2 reaction. The big obstacle to an SN2 reaction is steric hindrance, and tert-butyl oxide has too much steric hindrance to normally be good at an SN2 mechanism. On the other hand, it turns out that steric hindrance is not as big a factor for E2 as for SN2. So tert-butyl oxide can be better at doing E2 than at doing SN2. I'll discuss why steric hindrance is not a big factor for E2 in a later video in this series. Well, I hope you have memorized what happens in the single step for E2. Notice that E2 uses a base, not a nucleophile. So now we can update and say that the O- in this case will be a strong base. O- is in our strong base column. We want to label our alpha and beta carbons. We already labeled the alpha carbon, and it should be clear that carbon 2 is going to be our beta carbon because it's attached to the alpha carbon. We better draw in that beta hydrogen. I've drawn in the beta hydrogen on the beta carbon, and that indicates to us that carbon 2 is going to be the acid. Carbon 2 is the acid because it's going to give up its proton. And again, it will be a weak acid. Again, we just need to have memorized that the beta carbon in an alkyl halide is weakly acidic. The starting material is an alkyl halide, so its beta carbon is weakly acidic. I think we're ready now to draw the electron pushing arrows. First of all, we need an electron pushing arrow to show the base taking the beta hydrogen. So that arrow should go from the base to the hydrogen. By the way, notice that some professors prefer that you not put the tail directly on the atom. It's really best not to put the tail directly on the atom. Instead, you should draw in a lone pair and put the tail on the lone pair. So this is the arrow that shows the base taking the beta hydrogen. Remember, a base is an electron donor. So the base goes at the beginning of the electron pushing arrow. It should make sense that we want to put the negative formal charge at the tail of the electron pushing arrow. Electrons want to move away from a negative formal charge. Now we need an arrow to show the pi bond forming between the alpha and the beta carbons, and that arrow looks like this. We have to break the bond between carbon 2 and the hydrogen, and we use those electrons to form a pi bond between carbon 1 and carbon 2, and then we need an arrow to show the leaving group leaving the alpha carbon. So here's our arrow to show the leaving group leaving the alpha carbon. Now we can draw the product from this step. Don't start drawing the product until you've drawn all the electron pushing arrows. Always draw all the electron pushing arrows before you begin drawing the product. Here again is our method for drawing the product based on the electron pushing arrows. We have to look at this electron pushing arrow and ask, does this tell us to erase a bond, draw a bond, or both? This arrow tells us to draw a bond between the oxygen and this hydrogen. I drew a bond between this oxygen and this hydrogen, or at least I showed that they were bonded by writing them next to each other. Notice that I'm numbering this carbon 7 consistently with this picture. Since the oxygen is at the beginning of the series of arrows, we have to change its charge. This oxygen started negative and it lost electrons, so the oxygen becomes one step less negative and changes from negative to neutral. What about the positive potassium? In the starting material, the positive potassium is written next to the O-. Should I continue to write the positive potassium next to the oxygen in the product? Well, no. The oxygen has lost its formal charge, so the oxygen can no longer form an ionic bond with the potassium. Since the ionic bond is gone, there's no reason to write the oxygen next to the potassium anymore. And in fact, since the potassium plus is an unreactive spectator ion, the best thing to do is probably just don't write the potassium plus in the products at all. Now we're ready to work on this arrow. Does this arrow tell us to erase a bond, draw a bond, or both? Well, this is an arrow that tells us both to erase a bond and to draw a bond. This arrow tells us to erase the bond between carbon 2 and the hydrogen, and we already did that by moving the hydrogen onto this oxygen. And the arrow also tells us to draw a new pi bond between carbon 1 and carbon 2. This arrow told us to draw a new pi bond between carbon 1 and carbon 2. Now we're ready to work with this arrow. Does that arrow tell us to erase a bond or draw a bond or both? Well, this is an arrow that tells us just to erase a bond. This arrow tells us to erase the bond between carbon 1 and the iodide. So we can erase that bond and draw now. Now we can draw the iodide separately from carbon 1. So the tail of this arrow is on the bond between carbon 1 and the iodide. That tells us to erase the bond between carbon 1 and the iodide. The head of this arrow is on the iodide, and notice that in this picture, the iodide is already sharing the electrons at the tail. The electrons at the tail in this covalent bond are already being shared by the iodide in the starting material. Well, when the head of the arrow is on an atom that is already sharing the electrons at the tail, that arrow indicates that we're forming a new lone pair on the iodide. Most professors don't require you to draw all the lone pairs, so I'm not actually going to draw the lone pair, but we should know that a new lone pair has formed on this iodide. Now, because this iodide is at the end of the series of arrows, we have to change its formal charge. We make this atom that's gaining electrons from the last arrow one step more negative. This iodide started neutral, and it's gaining electrons, so it changes to negative. I've already changed the charge there on the iodide. What role did this molecule play in the reaction? Well, this is another alcohol solvent, right? Remember that an OH connected to a carbon chain is an alcohol solvent. And we would only use the alcohol solvent in the reaction if there was nothing better around. Well, we know this is better. And O- is more reactive than a neutral oxygen. So we're not using this alcohol solvent in this reaction. Instead, we're using the O-. What type of functional group is this starting material? Answer, an alkyl halide. What type of functional group is this product? Answer, an alkene. An E2 reaction is a way of changing an alkyl halide into an alkene. We followed these guidelines. Notice that we labeled the alpha and beta carbon. Always label the alpha and beta carbon for an E2 mechanism. In this starting material, there was only one beta carbon. There was only one beta carbon here, so we didn't have to choose between beta carbons. Again, make sure you have memorized exactly what happens in an E2 mechanism, because the hard part is how do you avoid getting E2 confused with SN1 and SN2. It's very easy to get SN1 and SN2 and E2 and later E1 mixed up with each other unless you have clearly memorized what happens for each of those reactions. So make sure that you have memorized what happens in an SN2 reaction, what happens in an SN1 reaction, and what happens in an E2 reaction. All of these things that you need to memorize, remember, are in this handout. It's important to understand the similarities and differences between an E2 mechanism and an SN2 mechanism. So let me ask you a question. How is an E2 mechanism similar to an SN2 mechanism? Well, here's my answer. The most important similarity between E2 and SN2 is that an E2 mechanism is a one-step mechanism, and an SN2 mechanism is also a one-step mechanism. You can see that here on the screen we have an example of the E2 mechanism we've been talking about in this video, and here's an example of an SN2 mechanism. And you can see that the similarity between these two mechanisms is that in both cases, both mechanisms occur in a single step. Next question, please pause the video and decide how is an E2 mechanism different from an SN2 mechanism. Well, here's my answer. The most important difference between an E2 and an SN2 mechanism is that an E2 mechanism uses a base, while an SN2 mechanism uses a nucleophile. E2 uses a base, SN2 uses a nucleophile. Well, that raises our next question. Let's actually think about both of these questions. These are very important questions, so I hope that you will pause the video and come up with an answer to these. How is a base similar to a nucleophile, and how is a base different from a nucleophile? I hope you actually paused the video and tried to come up with careful answers to these, because this is crucial material for your OChem success. Well, here's some answers. A nucleophile is similar to a base because they both donate electrons. A nucleophile and a base are both electron donors. You can see here that this base is at the beginning of the series of arrows, showing that it's donating electrons. And this nucleophile is at the beginning of the series of arrows, showing that it's also donating electrons. Okay, so if a nucleophile is similar to a base because they're both electron donors, how is a nucleophile different from a base? What would be your answer to that? That's a very important question. Well, you can see the difference from these definitions. The difference between a nucleophile and a base is that a nucleophile donates electrons to join another molecule. A nucleophile donates electrons to join another molecule, while a base donates electrons to take a proton from another molecule. You can see that from these examples. Here we have a nucleophile that is donating electrons to join this other molecule. And you can see in the product that the nucleophile has joined the other molecule. Whereas here we have a base that is donating electrons to take a proton from this other molecule. The base, you can see in the products that the base has not joined the other molecule. The base has simply taken this proton from the other molecule. To summarize, an SN2 reaction is similar to an E2 reaction because they are both one-step mechanisms. An SN2 reaction is different from an E2 mechanism because a SN2 mechanism uses a nucleophile, while an E2 mechanism uses a base. How are nucleophiles and bases similar and different? A nucleophile is similar to a base because they're both electron donors. But a nucleophile is different than a base because a nucleophile donates electrons to join another molecule, while a base donates electrons to take a proton from the other molecule. I encourage you to pause the video right now and take the time to memorize how a nucleophile is similar to a base and how a nucleophile is different from a base, because understanding those ideas will be crucial for your success in the rest of your OChem class. Now let me warn you against a mistake that I often see students make. Very often a student will look at a problem like this, and the student will use the table to determine that the mechanism should be E2. But even though the student knows that the mechanism should be E2, they forget about that when they're drawing their arrows, and they accidentally draw the arrows for an SN2 mechanism. I can see how that would be tempting, especially if you've just finished studying and practicing a lot of SN2 mechanisms. You might have just recently learned and practiced a lot of SN2 mechanisms, so it's easy to accidentally draw an SN2 mechanism even when you know the mechanism should be E2. One way to avoid that mistake is always write down the name of the mechanism that you're doing. If you write down the name of the mechanism, you're less likely to forget which mechanism you're trying to execute in the middle of the problem. And the other way to avoid making those mistakes is that if you know the mechanism should be E2, label the roles and notice that you're using a base, and make sure that you draw the correct electron pushing arrows for a base rather than for a nucleophile. Make sure you draw your base for an E2 mechanism taking a proton from the other molecule rather than joining the other molecule. Another important difference between an E2 mechanism and an SN2 mechanism is that E2 is an elimination mechanism, whereas SN2 is a substitution mechanism. Can you define those terms? How would you define elimination mechanism? How would you define substitution mechanism? Here's the answer. An elimination mechanism is a mechanism in which one or more groups are eliminated and no groups are added. A substitution mechanism is a mechanism in which one group is substituted for another group. For example, E2 is an elimination mechanism. In an E2 mechanism, two groups are eliminated and no groups are added. Can you identify the two groups that were eliminated in this E2 mechanism? Here's the answer. In this E2 mechanism, we eliminated the beta hydrogen and the leaving group. So two groups were eliminated, and there were no groups added to this molecule during the E2 mechanism. This is a mechanism where we eliminated these two groups from this molecule, and we didn't add any groups to this molecule. That's why we classify E2 as an elimination mechanism. On the other hand, can you see how this mechanism, SN2, is a substitution? Notice here that we're substituting this group into the place formerly occupied by the leaving group. E2, and as you might later learn, E1, are both elimination mechanisms. The E stands for elimination. And in both E2 and E1, there are two groups that are eliminated, the beta hydrogen and the leaving group, while no groups are added to the molecule. SN2 and SN1 are both substitution reactions. The S stands for substitution. By the way, the N in SN2 and SN1 stands for nucleophilic. These are considered nucleophilic substitutions, because the thing that substitutes into this molecule is a nucleophile. Again, an elimination mechanism is a mechanism in which one or more groups are eliminated and no groups are added. E2 and E1 are both elimination mechanisms. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.